Hello everyone. In this presentation, I would like to give an overview of transformer. Transformer is from paper Attention is All You Need by Vaswani et al., published in 2017. Originally, it is for natural language processing applications, specifically for machine translation. Although the architecture itself is generic, and nowadays it is also used for different other applications, including chatbots, vision applications, and others. For example, in this video, we use German to English translation. Before transformers, most deep learning for sequences like text used RNNs or LSTMs or GRUs. This model process the input and output sequentially like this. However, this kind of sequential model has problem to capture long-range dependencies, such as a word at the start may be forgotten later, especially if the sentence is long. Moreover, due to the sequential process, it is slow to train since there is no parallelization. Instead of processing things in order, they look at everything at once and decide which parts of the input are important. This mechanism inside the transformer is called attention. There is attention to self called self-attention. There is attention between the past output to input called cross-attention. There is attention between the past outputs also called self-attention, but for training we have trick called masked self-attention to focus only on the past outputs. Therefore, the model have global view from the start, flexible relationship since any part can connect to any others, and highly parallelizable, hence we can train on huge datasets faster. In this visualization, this part does not look parallelizable since we output one by one. However, the mask self-attention trick, which will be discussed later, can make the training in this part parallelizable. Let's see a bit more details the transformer's general architecture. The German sentence is first converted to collection of vectors using word embedding. Positional encoding is added to add position information for each word. Then, the encoder takes the input and encodes it into a context-rich representation. To extract that context-rich representation, each encoder block consists of multi-head self-attention module, followed by a fully connected layer and skip connection with normalization. We can have n blocks of encoders stacked on top of each other. The decoder receives the encoder's final output, and the translation ground truth or target sentence shifted one step to the right, starting with a special start token. This means that at each position, it uses the correct previous words from the ground truth to predict the next word. After a final layer and softmax, it outputs the translated sentence. Note that this input and output of decoder like this is only for training, so it can be parallelizable. For testing, since we do not know the ground truth, the input is the previous English words that has been translated, and the output is the next English word. Each decoder block consists of mask self-attention, multi-head cross-attention, fully connected layer, and skip connection with normalization. Like the encoder input, decoder input is also converted to vectors using word embedding, and positional encoding is added. We can have n blocks of decoder too. In original transformer paper, the number of encoder and decoder blocks n is equal to 6. However, technically, we can have different number of blocks between encoder and decoder, and we can also have different n to have shallower or deeper transformer. There are various extensions of transformer. We can use different kinds of input besides words. If image, the input is image patch. If audio, the input is chunks of sound. If DNA, the input is nucleotide sequences, and so on. Architecture-wise, we can also use only the encoder, like in BERT, or use only the decoder, like in GPT, and we will not go into details of these extensions in this video.